trying to be somewhat disciplined, I guess, about like working on these problems. You know, daylight's what do they call that? Daylight is a waste in here, so we gotta work, gotta work. All right. So I have a plan. There's the next step. So, right, trying to get more familiar with Clojure. Solving some of the easy problems. The last easy problem we did, I was struggling a bit, so I figured we should do another easy problem rather than... I was going to go to medium problems, but still trying to get familiar with the syntax and all of that. Best way to do it is to actually write some code with it. So, yeah, so that's what we're doing. And we'll just keep going, I think. What else do we want to do here? What else is there? Yeah, just keep going. I think we'll just keep going. That's what we're going to do right now. Wish to buy video games from the famous online video game store Myst. Usually all games are sold at the same price, $P. However, they are planning to have the seasonal Halloween sale next month in which you can buy games at a cheaper price. Specifically, the first game you buy during the sale will be sold at $P, but every subsequent game you buy will be sold at exactly $D, less than the cost of the previous one you bought. This will continue until the cost becomes less than or equal to $M, after which every game you buy will cost $M each. For example, if P is 20, D is 3, and M is 6, then the following are the costs of the first 11 games you buy in order. Okay, so all games are sold at the price P. A sale. First game you buy during the sale will be P. Every subsequent will be D less. Continue until it becomes less than the M, after which everything will cost M. Ah, okay, this is a neat problem. So this is like a linear, what do they call that? Linear sequence? What's the name of that? When you've got, it's actually two sequences combined, right? It's going to be, after a certain point, it's a constant sequence, and then the other, and up to that point, say, I guess a constant difference sequence, something like that. I'm not sure what the name of it is exactly, but it's an interesting thing. So what's interesting is we can do this. I'm probably going to ask, all right, you know, if, yeah, do you have enough money, or how many games can you buy? Oh, that's a little more interesting. I was going to say, so if you wanted to get the sum, well, you could still do this. It still works. Basically, you can write a function to compute, actually in constant time, how much it's going to cost you, given a certain number of games, how much the games are going to cost. So the way you would do that is the sequence. Basically, what you would do is you want to get this sum, or you want to figure out how many terms down you've got to go until you've hit M. So what that would look like is probably, could do a little bit of math to do that. So let's do that. This is a good problem. It's an interesting problem. See how we do. Oh, okay. Hey, okay. So there you go. That's constant time solution. Oh my goodness, man. That was so much more involved than it needed to be. But yeah, that's how you can do that in constant time. Very close to a closed form solution. Really very close. Very close. But yeah, the logical part, the part that I was really missing, is that you basically have like a cutoff. You have a parabola, and you've got two cutoff points, right? You can't use alpha that's less than 0, and you can't use alpha beyond this alpha equals k, right? And then you've got a few different variations of curves. So you can have a curve that looks like this for your this is sort of your money as you're buying things. It could look like that. It could look like this. I don't know. Could look like this. And it could look like this. And the differences between these, there's like some pretty key differences here. So if you hit this cutoff point, no matter what the reason, then you switch to the other curve, which is just a line downwards. But if you're in this range, you're this kind of curve where you're gonna go into debt before you hit this cutoff point. That's when you've got to employ the quadratic formula to figure out what is this first root, and that's the alpha. You're gonna pick the alpha just before that point for how many steps you're gonna go, and that's your total number of steps. Like obviously you're gonna go into debt beyond that, so you're not going to be you're never going to reach this point over here, right? You're nowhere close to it, and you can't add. Right. That's actually the point. So this happens before this point. Now, if this point, if you check this point and it's non-zero, this difference point, meaning there's some meaning you can actually reach here, and then you're going to switch to the next line. Well, then you have to operate as if you did reach here, and then you go from there. That's a simple calculation as well. It's because it's linear after that point, so it's a very simple calculation. So if you can reach here, you suppose that you do every time, no matter what the curve looks like. If you can't reach here, that means that you went under well before, and then you pick the point before you go under. So the logic is kind of simple, but I got kind of caught up in the weeds. That's how you can do this in constant time. Cool. We say we've got P, D, M, and S. Then we can define this K to be P minus M over D roof, or ceiling rather, ceiling of that. And then we can end up with a piecemeal function, piecewise function for the summation, which then we want to consider. We want to find alpha using this piecemeal function, and so this is diff k, which is S minus T of k, which is really F prime of k. Just diff k. I don't really know what to call this, but it's going to be F prime of k. So this function F prime of k, this value, is diff k. If that is less than 0, then we're going to be in case 1. If it's greater than or equal to 0, then we're in the third case. Yeah. It's not just greater than or equal to 0. I think it's greater than or equal to M. Okay. Wow. All right. That just kind of rocked my world, because all my calculations are wrong after that. The idea is the same, but this function that we started with has got to be different now. We got to reapply all this stuff. So first things first, this is K, we said is P minus M over D. Floor or roof is, I think this is still the same. Where does this come from now? P minus M over D is, yeah, that's fine. That's the same. That's the same. Right. If we go back to where we got K from, that doesn't change. See, it comes from this. Okay, so P minus M over D. And then, okay. It's confusing, but I think I understand. So, alright, we'll go back to our quadratic formula then. So, this is S minus alpha P plus D alpha minus 1 over 2 equals 0. This gives us D alpha squared over 2 minus D alpha over 2 minus alpha P plus S equals 0. And now what we want to say is you can multiply through by 2 and divide by D as well. Okay, so that's all well and good. That means we have square root of that, 20,601. Square root, right? It's about 143.5. All right, and now we're going to say D plus 2P plus that. D plus 2P plus square root of Q over 2D gives us approximately, so D is 19, P is 100, this is about 143.5, we want to go over, where's D? 19, okay. Which this is about 19 plus 200 plus 143 divided by 38. It's about 9.5. Yeah, about 9.5. All right. What? Excuse me? This is not. This is not 0. I think this is maybe part of the problem here. I think the issue is pretty simple, and that is that this curve hits 0 twice, and we're picking the larger. We should actually be picking the smaller one, I think. Right. Is that right? Because the larger one may be way past the cutoff point. In fact, there's 2 cutoff points. One of these is alpha's got to be positive, and alpha's got to be less than the cutoff point. So there's 2 positions. Oh, I see. You're actually trying to get the largest. This is so confusing. This is so confusing. I don't know, man. This is crazy. Come on, man. Oh my goodness. Oh. Excuse me. Excuse me. The reason why you're never going to pick the second one is because this is a negative value and this is a positive value, which means that what we ended up doing is we decreased our wealth, or we decreased how much we have to pay until it's actually negative how much. We decreased the price until it's negative, which, So what this means, if we're over here, is it means that we decremented the price from how much we have until we were in debt, and then the price that we were paying decreased so much that it became a negative number that we're paying, which now increased how much our total wealth until we're now out of debt. That's what we did on this curve following this. So we actually spent all our money, went into debt, and then the price went down, so then we paid back the money and went out of debt. That's why we can't use the second part of the curve, because it don't work like that. It don't work like that. Oh, it's really funny, man. It don't work like that. No, it don't. So really, we do want this one, actually. Holy smokes. How do you get a machine to figure all this out? You know, if you're going to write a piece of software that can write code like this, I don't think so. It's too much stuff to think about. That's so hard. That's hard. Alright, it's hard. It's really funny, but it's hard. It's probably doable. It's just really challenging. It's a lot of challenges, I guess. So we actually want this one every time. This one. That's the one.